All right, let's do it. Class recording is started. So, in the first two units that we've done so far, we first started talking about mechanics, and then we started talking about projectile motion. And in all of those instances, we are describing motion. We're talking about where an object is, what it's doing with its velocity, how is it changing with its acceleration, and then in projectile motion we described all those things but in 2 dimensions. So we answered those questions of where, what, and what next, but we didn't answer the question of why. Why do all these things happen? And chapter 5 gets us into why all those things happen, and we talk about Newton's laws of motion. So, in your Apple book, they try to build their chapters around themes. And you can see the theme, or the big idea as they refer to it, at the top of the packet that I gave you today. And so the big idea of Newton's laws of motion chapter is that all motion is governed by Newton's laws. And you guys have that in the big dark box right at the top of the page right there. So that's going to be our theme for this unit. All motion is governed by Newton's laws. So we're not just describing that motion anymore, we're explaining it. Why do these things happen? Okay? So, before we get into that, let's do a little bit of history. I know that's always a fun way to start physics class, But anyway, so let's talk about Newton. Newton is born in 16 crud. I want to say 1645 now, but I know that, no, 1642, I believe. Sorry, everybody. It's early, and it's Monday, so I really do know this, but yeah. So, I believe 1642, now if I remember correctly. So anyway, so first he was born on Christmas in 1642. And does anybody know who Neil deGrasse Tyson is? If you follow Neil deGrasse Tyson on Twitter, he's actually a pretty good follow on Twitter. He like tweets out jazzy little things, But there was one year on Christmas that he was trolling all the religious people by tweeting out things about a person being born on Christmas who changed the world and everything like that. And it's like Newton, So he got a lot of flack for that, but I thought it was kind of funny. So, but anyway, Newton's born in the 1600s, mid 1600s, and Newton actually was born in the same year that Galileo passed away. So there was these people were like, oh, this is like this cosmic passing of the torch from Galileo, whatever, maybe. So, but obviously, both of those, Galileo first, and then Newton, were part of this scientific revolution, right? Which is a part of a greater movement of the Renaissance, right? And when we talk about the Renaissance, the one big thing that comes out of the Renaissance, or that sort of sparked the Renaissance, is this idea that people start thinking for themselves. Because up until that time, for about 1,500 years or so, there was one answer to any question that you asked, right? And that answer was God. Why do these things happen? God. Why are we doing it this way? God wants us to do it this way. That was it. That was the answer to every question. And so after a while, people are like, maybe there's more out there to that. And it starts early, back in the 1400s and early 1500s, with people like Copernicus and Kepler. But one thing that made them a little bit different than Newton, and mostly Galileo, sorry. Galileo was the first guy to go out there and basically slap his name on it and say, yep, sorry, God's not the reason why this is happening. Up until that point, scientists would sort of put those things out there sort of in private. Copernicus, I know, are you guys familiar with Copernicus? First person really to kind of publish something that says the planets go around the sun, not that everything goes around the Earth. He wrote that book and published it about a month before he died, because he was actually trained as a monk, basically. And so if you're a monk and you go out there and print a book that says, hey, maybe God isn't the center of the universe, they don't like that so much in the church, so you wait until you're almost dead, and then you're like, okay, yeah, here it is. So, same thing with Galileo. Galileo was out there saying these things, and finally the Pope decided, hey, you need to be quiet. So he sent him to, he was in house arrest. Galileo spent the rest of the end of his life under house arrest because the Pope didn't want to kill him, because, killing an old guy doesn't look so good when you're the church, It doesn't look good for anybody really, but, the church especially, so. But anyway, by the time Newton comes around, we're into this idea of the Reformation, and people are a little bit more free to speak their mind, and the evidence is there to back up a lot of those things that they're saying. So, Galileo lays a lot of the groundwork, and then Newton sort of picks it up from there. So Newton was born in 1642, goes to college, he goes to Cambridge first, I believe, if I remember correctly. And then he's there for about a year, and then he goes home back to his family's farm because the plague is running through England. Oh, Newton's English, sorry. Sorry, I forgot to throw that stuff. Newton's English, and so the plague starts rolling through Europe, and especially England. And so the university basically sends everybody home because large groups of people, easy transmission, all that stuff. So Newton's smart, and he goes home. Farming really isn't his gig, so from what I understand, he just kind of sits around the farm and watches everybody else farm, I guess, and sort of just observes, figures things out, blah, 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 and then allegedly one day the apple falls from the tree. Allegedly. I don't know. I wasn't there. I don't know if it happened. I don't know if it hit him in the head. I don't know if it actually fell from the tree. I don't know. But anyway, a spark of innovation allows him to put all these ideas together, and he may or may not have invented calculus along the way, just because he couldn't fit the math that was available to them. So, the math of the time wasn't exactly working for him, so he invented his own math, which you could maybe try in math class sometimes. You can't figure out a problem, just be like, I invented my own math, just like Newton did. So his works all the time, yours might not. So just, give it a go, see what happens. Anyway, so he's at his farm, and, everything's going great. And then the plague sort of runs its course, and he goes back to school. And he's back at school, he becomes a professor, and then about 20 years later, after he was on his farm, he's working as a professor, and so he's there, and he's got a job and everything like that, and he makes science friends, and one of his friends is Edmund Halley, Halley's Comet. Are you familiar with Halley's Comet? So the guy that it's named after, he didn't really discover it, but it's named after him. He and Newton were like bros. And so Halley found these things that Newton was sort of working on while he was on his farm, and says to Newton, hey, what's this stuff? And Newton's like, I don't know, it's some things I was working on, ideas, blah, blah, blah. And Halley's like, yeah, this is pretty good. You should probably like publish this. And he was like, okay. So he writes a book called the Principia Mathematica, mathematical principles, in Latin, because that was the language of the time. And, it's basically the stuff that you guys learn today. So back in 1687, Newton publishes these things, and here we are almost 350 years later still talking about it. Why? Because it still works. It's still true. These things that we see in our world, things that Newton would have never imagined, like sending a rocket ship to the moon, or sending satellites to faraway planets and out of our solar system. They're all governed by the three things. And actually, there's a fourth one that we'll talk about in isolation. We talk about gravity. But all these things that he figured out like 350, almost 400 years ago, here we are, still doing them because they still work. So that's sort of Newton's deal. You may learn of him as Sir Isaac Newton. He actually was knighted a little bit later in his life for doing some politician-y sort of things, not for like figuring out, how the universe works. That was we signed some treaty with France though, and I suppose that's enough to get a knighthood, I guess, because that's really all that happened, right? England and France like signed treaties and then went to war. Like that's basically European history for 200 years, right? So that's my understanding of it, I guess. So, what else? Oh, Other things that happened to Newton, there was a little while that he kind of went crazy, but he like came back. So he was, in addition to, doing the laws of motion stuff, which at the time was not like, when he wrote the book, it wasn't like, oh wow, this is some great revelation. It was kind of like, okay, like whatever. Sure, well, we get to Newton's first law, like, we'll talk about that. But he also did some things with light, and also he did some alchemy. Are you familiar with alchemy? Because at the time, alchemy was like a legit venture, like, because we didn't know about protons and neutrons and stuff like that. It was like, I could turn this hay into gold, no problem. Like, but yeah, it was like a really legit venture. Like, so that was like a scientist as you tried to do these things. But one of the things that he experimented with, because most alchemists did, was mercury. Because mercury is cool to experiment with if you've ever like gotten a chance to. But it does cause some brain damage, and you get mercury poisoning, just a little bit. So, which is also where the expression, like in Alice in Wonderland, the Mad Hatter, haberdashers used to use mercury to make their hats shiny and give it like a kind of gleam or whatever, before they knew that it was, caused brain damage. So that's why the expression of the Mad Hatter, because a lot of hatters were actually crazy because they had brain damage and because they would use mercury and stuff. So Newton had a little bit of that going on, but he came back, and so anyway, that's the story of Newton. So, all right, so let's talk about a couple of Newton's laws here, and it's always best to start at the beginning. So let's start first with Newton's first law. So Newton's first law is probably one that you have heard before. Actually, you know what? Let's go back up to this part right here. All right. So Newton does not invent the idea of a force, but what Newton does is more clearly define what force does. So you guys can see right up at the top of the page there, you have a definition for force. It says, in short, a force is a push or a pull, which is great. In short, a force is a push or a pull, which is great. And yes, that is what force is. But more importantly than what force is what force does. And what Newton realizes is that force causes acceleration. Force causes acceleration. So yes, forces are pushes and pulls, and even the ancient Greeks knew that. But what we didn't realize, or what they didn't realize, is that forces cause acceleration, and that's the big idea that we need to take out of this unit. Forces cause acceleration. So, let's talk about what Newton realizes making all of his observations and what sort of he puts together about the behavior of objects under the influence of force. So, Newton's first law. And you can see there, Newton's first law is summarized with 2 key points. And how do I know they're key points? Because there's keys right next to them. That's how your Apple book distinguishes those key points. So it says, and like I said, you've probably heard Newton's first law before. An object at rest remains at rest as long as no net force acts on it. An object moving with constant velocity continues to move with the same speed in the same direction as long as no net force acts on it. Right? So an object at rest stays at rest, object in motion continues in motion. And we use one word to sort of summarize these ideas. What is that one word that summarizes these ideas? Hopefully you've heard this before. Inertia, right? So inertia is a property of matter, just like Bill Nye told you right at the beginning of this show. So what does inertia mean? Well, inertia means this. Objects don't start moving on their own, which is easy. That was an easy part of Newton's first law. It's easy to convince somebody that, it's on the first page, right in the middle of the first page, or right above the key points. So there's 2 parts of Newton's first law. The first part is objects don't start or stop moving on their own. Right? Easy to convince somebody that objects don't start moving on their own. Anybody who has seen something just sitting there on the table has never seen it start moving spontaneously by itself. Right? That's an easy part of Newton's first law. But this stop moving, right? Because up until, well, now, even for the entirety of your experience on this earth, anytime you have seen something moving, what does it eventually do? It stops, right? Anything that is moving stops. So before Newton, the prevailing idea was, oh, something at rest or being at rest is like a quote-unquote preferred state of motion. Things that are at rest don't start moving. Things that are moving end up stopping. So at rest must be where it's at. And that's kind of like what the Greeks thought. It's like, okay, well, things must stop, but that must be it. And Newton comes along and says, no, that's not it. Things don't change. Things that are at rest stay at rest. That's fine. But things that are moving actually want to keep moving. They stop because something makes them stop. And that was a big idea. That was harder to convince people of because we'd never seen it before. Okay? But when you start thinking about it, it's like, oh, well, that's why this happens, right? If we think about, like, just running, okay? It's much easier to start running and continue running than it is to start, stop, turn around, come back to where we began, stop, turn around, go back to where we go, stop, turn around, like going back and forth. That's harder to do, right? Yeah, we'll leave it at that, right? Are we okay with that idea as far as inertia goes? Okay. So, right? Newton's first law is known as the law of inertia. This tendency of an object to resist changes in motion is referred to as inertia. The idea that objects want to continue doing what they are currently doing, whether that's at rest or whether it's already moving. Okay? Good there with that idea? Okay, so practical application, because the question comes up, why do I have to learn this stuff? Well, here you go. I'm giving you a chance, all right? So this week, right, just got done with the grading period, probably working hard, you know. Halloween's this week, and then, you know, we got the World Series going on and stuff like that. So this weekend, probably, you're going to want to catch up a little bit, you know. So maybe, you know, Saturday morning, you decide, I'm gonna sleep in, all right? So you sleep in, and you roll downstairs at the crack of, like, noon 30, you know, and Mom starts giving you some grief because it's noon 30 and you just woke up, you know. So you can be there and be like, Mom, it's not my fault. I learned in school that objects at rest want to stay at rest. I should still be up in my bed right now. It's literally unnatural that I'm down here talking to you. So give it a go. See what she says. She might slap you. I don't know. But you know, be like, Mom, I learned it in school. Like, I'm learning stuff. So give it a go. See what happens. All right? Okay. Next here, this conceptual example to illustrate the idea of inertia. Okay? This is one of those problems that shows up in like every physics book ever written in one form or another, so I would feel remiss if I didn't explain it to you. Okay? So here it is. A heavy anvil, which all of us have seen before in cartoons, but no one has actually ever seen in real life. So, are you like a blacksmith, or? Because that's really what it is, like blacksmiths, you know. Because but I mean, unless you've ever been to Hale Farm before, have you ever seen a blacksmith? I guess that's anyway. What?
Amish country?
Yeah, like Amish country, Hale. Oh, sorry. You haven't lived here your whole life, so there's this place down south. It's not quite Amish country, but it's kind of called Hale Farm, and like every like elementary school student in northeastern Ohio goes to Hale Farm at least once in their lifetime, you know, for a field trip. And it's like an old timey village, and people still like, you know, do blacksmithy things and, you know, farm and, you know, that kind of stuff. So, but yeah, like it's basically like Amish country, but like full time, and then people get in their cars and go home at night, you know, because it's like their job to work at Hale Farm. So. All right, so it says, Heavy anvil hangs from a string attached to a ceiling, as shown on the right. An identical string hangs from the bottom. Which string breaks if you pull the lower string downward rapidly? So, everybody have the gist of this setup here, right? So, anvils hang from the ceiling, have a string. We yank the string really quick. One of the strings will break. Which one will it be? Top or bottom? Bottom. And here's why. All right? The anvil is hanging there, and it has inertia. It doesn't want to go anywhere. So if we yank that bottom string real fast, the bottom string starts to move, but the anvil wants to stay where it is because of its inertia. And so the bottom string will break because the anvil's inertia will prevent the top string from moving. Does that make sense? You okay with that? Does this experiment work as well if, say, if we like hung a golf ball from the ceiling? It wouldn't work as well, right? Because of one of the properties of inertia. Okay? All objects have inertia, but how much inertia do objects have? And the answer is, it depends on their mass. The more mass something has, the more inertia it has. So mass, we've learned that tells us how much matter something has, right? You know, how many atoms are there and stuff like that. Okay, but mass also tells us about inertia. The more mass something has, the more inertia it has. Okay? There's a ridiculous problem from another book that I use sometimes about you being on safari and you anger an elephant or a rhino. You could do that, or hippos, because hippos are hippos are very aggressive from what I understand. I've never, you cross a hippo, they don't like that very much. So, but anyway, so if a large animal starts chasing you, right, you run away, but you're supposed to, while you're running away, run in a zigzag pattern. Okay? The more mass that animal has, the more inertia it has. So if it's chasing you, you're running this way, and then you turn and go this way, the animal has to turn and go that way, but all of its mass and all of its inertia is telling it to go straight. Does that make sense? All right? Yes, no? There's some confused books. That change of direction is fighting inertia. Inertia says go one way, go one way, go one way. The same way that we're already going. But if you keep changing directions, that's hard for something that has a large amount of mass. Okay? Good there? Okay. So that's Newton's first law. Newton's first law deals with inertia. So, let's talk about Newton's second law. Right? Just to quickly review. So, Newton's first law. Objects don't start or stop moving on their own. Object's motion does not change. Starting, stopping, changing. Those are three things that we use to define what term back in the first unit on mechanics. Starting, stopping, and changing. Those are three forms of acceleration. Newton's first law says none of those things happen on their own. Acceleration doesn't happen on its own. We have to make it happen. So, Newton's first law deals with inertia, things not changing, not speeding up, not slowing down, not changing direction. So, if inertia is things not changing, and Newton's first law deals with things not changing, Newton's second law is going to deal with things changing. Right? So, if Newton's first law is summarized with the term inertia, acceleration applies to Newton's second law. So it says here, the second law of motion is more specific than the first law. It tells exactly how a force changes an object's motion. And changes an object's motion, right, is our definition or a description of acceleration. So, Newton's second law. is best summarized by this equation. F equals ma. Force is equal to mass times acceleration. It might not be the most famous equation in science. That's probably E equals mc squared, okay? But this one here is one you deal with a lot more than E equals mc squared. This affects your daily life continuously, all right? So let's talk about what it means. F equals ma, we can rearrange it to look like this. Divide both sides by m, yes? Okay. This equation, or this version of this equation, tells us how acceleration is determined by two other factors. So you can see the heading across the top there. The second law relates force, mass, and acceleration. So what this is telling us here is that acceleration is determined, the acceleration of an object, how much it actually changes, is determined by two factors. The force acting on it and the mass of that object. And here, it says acceleration is proportional to the force and inversely proportional to the mass. And hopefully you can see that from this equation. With where force and mass are, right, they're a fraction, and then fractions are division problems, right? And then acceleration is the answer to that division problem, right? If we make the top of the fraction bigger, if we make force bigger, what happens to the answer to that fraction problem, or that division problem? If the top of the fraction gets bigger, what happens to the equivalent, or the answer to that? If the top gets bigger, right? If we go like 1/4, 2/4, 3/4, right? The top of that fraction gets bigger. That's a bigger portion of the pie, right? That's a direct relationship. Top gets bigger, the answer gets bigger. But if the bottom of the fraction gets bigger, right? 1/2, 1/3, 1/4, 1/5, the bottom of that fraction keeps getting bigger, but that's a smaller portion of the pie, right? That's an inverse relationship. So acceleration is directly related to force and inversely related to mass. And these two pictures that are on the back of the next page illustrate that idea, right? So the top one, like it says, right, figure 5.3, acceleration is proportional to force. If we're going to see that, though, we need to keep the mass constant. So in this case here, we're pulling with a certain amount of force that is being measured by this little meter right here. And like it says here, if we double the force, we end up with double the acceleration, as long as we keep the mass constant. All right? But then, okay, here, if we have a constant force, same force applied in both instances, if we make the mass bigger, going from 1 to 2, we end up with half of the acceleration. So the heavier things there are, the less they accelerate, right? The more force we use, the more it accelerates. Good there? All right. We'll wrap it up here for today. We'll look at some examples of Newton's second law tomorrow in class, and then we'll also discuss Newton's third law, and we call that action-reaction. All right?